For coming to this Tech Talk. I got to tell you that I am truly excited to have Dr. David Auslander here. You know, I was at Berkeley when I met Dave. I was a material science major doing my graduate work, and I thought, I'll take a fun class and something outside of my field. Let's take a mechanical engineering course. I kind of looked through the catalog and thought his sounded the most interesting, and I sat in on it, and wham, two things happened. One, I regretted studying material science instead of mechanical engineering. And two, I said, when I get out, I'm going to go find jobs in mechanical engineering. And that's what I'm now doing here at Google. It's what I've done in my previous job. And so, Dave, I just want to say thank you. I really love this line of work, and I've been so excited to bring you here, because not only is it something dear to my heart, mechanical engineering, but it intersects so well with what so many people here at Google do, which is programming. So please help me welcome Dave here for the Tech Talk.
This mic on? Okay, good. Okay, thanks very much. Just as a matter of interest in that regard, I think we have some mechanical engineers over here, right? What kind of background do we have for any other mechanical engineers? No, okay, we got the whole mechanical, we must have the entire mechanical engineering contingent of Google here. Electrical engineers? CS? English? Okay. Yeah, right. Okay, what I'd like to talk about is what's generally referred to as the area of mechatronics, a mashing together of mechanics and electronics, and otherwise known as mechanical system control, and kind of my view of the software perspective on mechatronics and mechanical system control. First of all, the name Mechatronics goes back to the early 1970s. It was originally coined by Yaskawa Electric, describing, at that time, the brushless motor, sometimes called brushless DC motor, sometimes called brushless AC motor. They actually trademarked the name for a while and then gave up the trademark, and the name has come to mean the synergy of putting mechanics and electronics together to get something that you simply couldn't conceive of otherwise. I say don't take the name too seriously, because what's happened in the interim has been the addition of software to this, which has changed things as dramatically as the initial addition of electronics, perhaps even more. So what the general theme here is that the value added in mechatronics is really software today. And so that's what I'd like to focus on. If we look at mechanical system control, and I'll give a little history in a moment, if we look in the past, the issue was how do you build complexity into mechanical systems? If you look at the present, the issue is how do we manage the complexity we have? So we've gone from scarcity, in some sense, to too much, and that's really the whole issue of how to deal with mechanical systems. So there's been a long history. Complexity has been something people in mechanical systems have looked for. We're looking here, and when I talk about control in mechanical systems, I'm looking at the issue of modulation of power for delivery to a target. Okay, so that's what I'm calling a mechanical system. Any kind of system in which real physical power, in some sense or another, has to be delivered to a target. That's a mechanical system. I mean, people in some other fields might disagree with me, like chemical engineering and such, but I consider all of that to be a mechanical system. So motion systems, so when you think of mechanical, of course, you think of motion first, but thermal systems, fluid systems, chemical systems, they all come under this. And the thesis here is that software has made this whole field into an entire new game. It just is totally different than what you would look at, say, 25 years ago. It's a completely different field. All the rules have changed, as have the potential. Okay, so a little bit of history, I think, gives some perspective in terms of this complexity issue and how things work. And I'll look here just at three interesting precedents: steam engines, the Jacquard loom, and the DC motor, just to give a little feeling of complexity, control, computing, and how this was done historically. This is the remains as of 1880 of a steam engine that was built in 1760. The purpose of the this particular engine was to pump water from coal pits. Okay, so you're looking at 18th century technology. Okay, and the interesting thing from my perspective, so this is actually early 18th century. Okay, so Newcomen invented the steam engine 1712, a so-called atmospheric steam engine. And what's interesting here, the way this engine works, you have a chamber, you have a fire, you have a boiler, steam goes into the boiler. At the appropriate time, you close the valve and squirt water in here, cold water. And when you squirt water in here, the steam condenses, lowers the pressure in the cylinder, pulls down the piston. Okay, and that, of course, on this side operates a pump. Okay, so it's an so-called atmospheric engine because the pressure difference across the piston can obviously never exceed 1 atmosphere. What's of interest here is this area right here. This is kind of the equivalent of what you might call an 18th century FPGA. Okay, this is where you built the controls and complexity, and the object here is all of this mechanical gadgetry is to open and close valves at the right time. So you have to open the steam valve, close the water valve, let the steam in, then close the steam valve and open the water valve and let the water in for the right amount of time, then close that valve, and that makes the engine run. Okay, so you've got a basic system running on what we would call control logic. Of course, all built in to the mechanical gadgetry that runs the engine. This is a somewhat later steam engine. So this is a 19th century steam engine. Came out of a cotton mill, okay, and at this point just sitting out in a field someplace. The interesting thing on this engine to look at is right there, okay, the flyball governor. And that gets us into a lot of issues of computation. I should mention, by way of giving my biases, that I'm in mechanical engineering department at Berkeley, but I do controls. Controls is my main interest. So if I get a little biased and more interested in the controls part of things, that's why. If we blow up this a little bit more, here you see the classical Watt governor. So the Watt in Watts comes from James Watt, who was a steam engine manufacturer in England. He invented the Watt governor. What happens here is this shaft over there is connected to the main drive shaft of the steam engine. As it spins, these flyballs spin up and down. Okay, so centrifugal force drives them up. And this linkage over here, that linkage connects to the steam valve. Okay, so as the flyballs go up, because the engine speeds up, it closes down the steam valve in order to keep the steam engine at constant speed. Okay, so up to pre-computer days or pre-electronics days, so middle of the 20th century, this kind of represents the state of the art in feedback control in mechanical systems. The interesting thing to note and to keep in mind here is that power passes from the shaft through the flyballs, through the linkage, and is used to operate the steam valve. Okay, that's an important thing to keep in mind as we move forward, that there is a direct power path all the way from the sensing all the way through the computation and to the actuator, in this case the steam valve. Okay, here's another type of computing. This is a lot more like what we would call modern digital computing. This is a loom, Jacquard loom. Again, 19th century, very early 19th century. What you see over here are punch cards. They're wooden cards about this big, punched full of holes. And what those holes do is give you the patterning on the loom. So the patterning on the loom is controlled by those holes. That's a piece of silk woven on a Jacquard loom. The threads on that silk, in this case, are actual gold and silver threads. This was done in Japan. And so that loom is capable of a pattern that looks like that. And so again, when you talk complexity, pre-computer, pre-electrical, pre-electronics, when you talk complexity, you really are dealing with quite significant degrees of complexity. This is just kind of for fun. This is a a steam valve in a lab at Berkeley, still functioning, still in use, 1893 steam valve. Again, if you look here, the sensing is all done mechanically. And again, think of it in modern terms. The question is, how do you get that information out of there? Right? Well, there's only one way to get it out visually. Yes?
Does that valve operate with a metallic diaphragm of some kind?
I've not looked inside it. It's way up on the up near the ceiling in the lab.
I'm just wondering how accurate it might still be.
I don't know. I mean, most of the valves of this sort are the bent tube. So you have a bent tube, closed tube, and as the pressure goes, the tube tends to unbend. That's the way most of them work, but I've not looked inside that one. I have no idea how accurate it is. But as you can see, it's telling the pressure there, happily in use for 120 years or so. Okay, electrical motors. Okay, keep in mind this power path business again. This is the classical Faraday motor, 19th century. The way a brushed DC motor works is you've got your permanent magnets. Okay, so you've got permanent magnets. You've got a coil. If you run current through the coil, you get a magnetic field. If the magnetic field crosses the magnetic field of the permanent magnets, you get a torque generated, or a force is generated, and it moves. But if you don't change the electric field in the rotor, it will move and stop, because it'll just come to equilibrium with the field of the permanent magnets. So you've got actually a split in the coils, in the wires that deliver current to the coils. And as you cross this split, you simply reverse the current. Okay, now this shows only two pieces. This is called the commutator, shows only two pieces. A modern motor has lots more than that. But the idea is the same. So as you're about to come to equilibrium, well, you flip over on the brush, you swap the current, current goes in the other direction, and the motor keeps going. Okay, and that's how you get a motor that keeps turning when you've got a DC current driving the motor. So if you look out here where you're driving the motor, you just see standard DC. Okay, so you just see a current in one direction. But by crossing back and forth across the commutator, you keep reversing the current, the motor keeps turning. Now, the interesting issue here is, again, think in the terms of the Watt governor. You're delivering power to the motor through the element that is sensing position, because this is connected to the rotor, and doing the computation. The computation here is which direction should the current be going as a function of the position of the motor. Okay, so you're delivering power directly through the element that's doing the sensing and the computing. Okay, and this is the classical brush motor. Millions of them around. You're still in use. They're all over the place. So still a very common engineering component. Okay, so that gets us to the classical control of mechanical systems. The issues here that we're dealing with, no separation of sensing, computation, of power. Okay, so we've just been through that. That's the issue. Okay, so early 1970s, Yaskawa, dealing with the brushless motor, invented the term mechatronics. Okay, the idea was that if you added electronics, you had something that was totally different than anything you had had before. So here's a brushless motor. Now, what you do in the brushless motor now is separate these components. So you invert where the permanent magnet, green is still a permanent magnet, but it's on the rotor now, and the coils are on the stator. But notice no brushes. Brushes are gone. In their place is computation, sensing, and amplification. Okay, so what you've done in order to make a brushless motor is separate out sensing, computation, and amplification. And that's, of course, why electronics made the whole control of a mechanical system a completely different animal. Now you're free to optimize to the best of whatever you've got. You can optimize sensing, you can optimize computation, you can optimize amplification using whatever technology is available to you. Whereas in the previous system, you needed a low impedance path all the way through the system in order to transmit power. And so you couldn't do that. Okay, so this system motor works by exactly the same way. When the position gets to a certain point, you change the current. And so nothing has changed, except with the absence of brushes, I can make a motor that in the same space generates a lot more power. Because the power in the brushed motor is primarily limited by the voltage, and the voltage is limited by sparking on the brushes. If I push the voltage up too high, I'll get more sparking on the brushes. More sparking on the brushes, they wear out. Lots of high-frequency RF frequency noise. The brushes burn up, etc. So you have maintenance problems. So your voltage is very much limited on a DC brushed motor. Here, your voltage is not limited. Run your voltage up anywhere you want. High-performance motors of this sort in servo systems will often run 200 to 400 volts. So you can run these at quite high voltage and get a very, very compact package in terms of the power per unit weight. Okay, so that's the brushless motor. Okay, then that gets us to what you might call the last third or so of the 20th century. At that point, you add in compact computation. Okay, so the development that gets added in at that point is compact computation. And these are a couple of definitions. This is what happens when you let a committee define something. I much prefer for mechatronics a rather simple definition, application of complex decision-making to the control of physical systems. And that's kind of what I use for mechatronics. We get there to this kind of decision because of compact computation, small and cheap. Okay, so where we go today, control complexity is now limited only by software complexity. Notice how much compute power you want to buy is your only limit in complexity. So that goes back to my first comment that we've now inverted the problem. Is in the earlier systems, as you see, the problem of building complexity into the system was the issue. How you do that was really difficult. Anybody ever seen the inside of a mechanical calculator? Okay, they're wonderful gadgets. Okay, and four function calculators, they were common through the middle of the 20th century. Every office that needed to do computation had them. But it was a device about this big. Okay, and just absolutely filled with gears and linkages and cams, and unbelievable. It worked. That's what the Wright brothers did, by the way. I mean, before they got into the airplane business, the Wright brothers did adding machines. Another issue, which I think is less important in this audience, but in most audiences I speak in the academic world, if you say control, people think you're talking about feedback control. Feedback control, which is another subject, is of great interest to the academic world, because the mathematics of feedback control are rather complicated and interesting. And so control in the academic world usually means feedback control. In this case, I'm interpreting control much more broadly in terms of all of the things needed to coordinate the motion of complex machinery. So when I say control, I don't mean just feedback control. I mean control interpreted broadly in terms of machinery. Okay, so if we look at enabling technologies in going from classical mechanical control to modern mechatronics or mechanical control, the first one is amplification. And we are direct descendants of the vacuum tube, basically. The vacuum tube gave us electronic amplification, and we have followed through into solid state, but the idea is basically the same. An interesting side development that really falls into this category that I've never seen anybody follow up on is the pneumatic, particularly the pneumatic controls, anywhere from early part of the 20th century all the way through the 1970s and even into the 80s. If you went into process plants, you'd still see pneumatic controllers. Pneumatic controllers were based on something called a flapper nozzle valve. Turns out if you look at a flapper nozzle valve, it is really a pneumatic operational amplifier. It's really quite an amazing device. And it allowed pneumatic controls to have full independent computation of derivatives and integrals and proportioning Yeah.
Is this another word for fluid logic, or would you consider?
No, fluid logic. A flapper nozzle valve is mixed logic. Flapper nozzle valves are rather simple. If you imagine a chamber, pressure, and a little nozzle, and then a flapper. Okay, and what happens is small motions of this flapper will change the pressure in that chamber. And that's the whole basis of a flapper nozzle valve. Fluidics is all fluid, no moving parts. So this is a mixed technology, but way, way earlier than fluidics. So fluidics was a 1960s invention. And so this is like 1910 and even earlier. Okay, so amplification enabled the isolation of measurement, computation, and actuation. What you want to do is mismatch impedance so you do not transmit any more power than you absolutely have to across each of these interfaces. Okay, then the second is the emergence of software. Originally, software was applied in the process control industry for the very simple reason that they could afford it. You had large, expensive hardware, improved productivity and reliability in that industry tremendously. The kind of computers we're talking about, we had one in my lab when I started in Berkeley of this sort, just to give a feeling for what we're looking at. The computer had 18-bit words, it was a PDP-7. At the time, we expanded the memory, which was a big deal. We added 8,000 18-bit words, and the cost for doing that was about $30,000 in 1960s dollars. So, you know, you can see why only the process industry could afford it, but they were willing to spend that kind of money, and it made a big difference. The invention of the microprocessor dramatically changed the cost of entry. And now, if you look at the issue, if I have any system in which I'm trying to modulate power, the cheapest way to control it today is with a computer of one sort or another. So now, this is the least common denominator. If you want to control the modulation of power, the only time you normally will find that kind of computation being done in something other than a computer is where you have speed limitations. So you go to either analog or FPGA. Okay, real-time software is the key to mechanical system control. If we look at the general notion of software, the magic of software is it's data reproducible. If I run a program once and run it again, I get the same answer. Okay? This, interestingly, really from the perspective of people brought up in the world of analog systems, is magic. You have a system in which there is no error propagation. With no error propagation, there's no complexity limit. And this is true magic. I mean, if you're brought up in the computational world, for example, anybody here know what an analog computer is? Oh, okay, a few. That's more than I get most places. But if you're brought up in the world of analog computing, okay, analog computing complexity is ultimately limited by signal-to-noise ratio. In other words, if you're willing to spend enough to keep the signal-to-noise ratio high or noise-to-signal low, keep the noise down, you spend a lot of money. Ultimately, though, that noise will propagate everywhere, and if you go too far, you're going to get nothing but noise. This is not so in digital systems. Okay, digital systems don't do that. And it's the magic of, you know, you have to think back to the 1930s when the basic binary representation was developed. And it had to be idiotic. Right? To think in the 1930s when vacuum tubes were really your only means of amplification, that somebody said, let's carry 1 bit of information per wire, instead of an analog signal which could carry, depending on, again, signal to noise, you know, anywhere from 10 to 15 bits of information on that same wire. And you're dealing with tubes. I mean, your smallest unit, you know, is about that big for a vacuum tube. And some idiot says, let's put 1 bit per wire. You know, it has to be crazy at the time, really crazy. But what it did is define a domain in which error doesn't propagate. And that domain is indeed truly magical. It makes all the difference. However, okay, software is not time reproducible. okay, in the general computational sense. And so if you look here, for example, a very simple histogram of how long it takes a program to go around a loop. Okay, so you just write a loop, nothing but a loop, and each time around the loop you time how much it takes, and then you take that timing and you drop it into a histogram. Okay, and here you can see in this particular computer at this time it was taking about 4 microseconds most of the time. Okay, overwhelmingly most. Okay, so certainly from an average point of view, the performance was very consistent. But not from a detailed point of view. Okay, because look out here, where you begin to get outliers, these numbers are way off. They don't reproduce at all. Okay, and you can get a system that will run 4 microseconds most of the time. Okay, and look at where you're out here. You're out at half a millisecond.
So what sort of system are you talking about here? I mean, is this
Windows.
So what about like DSPs and things?
What's that?
What about DSPs and so forth? The kinds of things you see that run motors.
That's where we're getting. Okay, so the issue is what's between you and the processor. Okay, and how do you design your software? This is not a function of the computer, the bare computer. Right? What you're seeing here is a function of the operating system environment. Okay, but nobody lives without some kind of environment. Right? You can't do anything complex without some kind of environment. And so the question for real-time software is, what kind of environment do you want to have? Okay, so where are we in real time for mechatronics control? One of the interesting things, again, if you look at the real-time community, is a lot of effort in the real-time community goes into what's called hard real-time. And hard real-time is defined as something with an absolute deadline. If something does not happen by some deadline, the system is considered to have made a major error. Hard deadline in terms of mechatronic systems is not common. Most of the time, statistical timing, that is statistically reproducible timing, gives you adequate control for most mechatronic systems. The other problem with the real time is that in a mechanical system, a lot of the activity is asynchronous. And therefore, you can't do deterministic scheduling. So again, what happens inside the processor becomes statistical, as distinct from hard real-time, which cannot be statistical, has to be entirely deterministic. Okay, so where that gets us is to a fundamental design principle. And that is, if any mechanical components are present primarily for the purpose of transmitting information, think about replacing them with software or electronics. Okay, and think, for example, well, here are the ones that we just talked about with a little addition. So we took a DC motor and replaced a brush with a brushless motor. Okay, and the brushed motor, the commutator is used to transmit and compute information. The brushless motor, that's done in a separate component. Look at the modern automobile. The carburetor is used to meter fuel. That is, to provide the correct air-fuel ratio to the engine regardless of the operating condition of the engine. The carburetor is very much in the same mode as, again, you're talking late 19th century for the carburetor, the same mode as the brushed motor. The computation, the sensing, and everything is all wrapped up into the same components. I've never personally taken one apart and tried to adjust one, but I've seen it done. Okay, and it's a nightmare. It's a real nightmare to adjust one of those things. So we replace that with fuel injection. The injector is dumb. Okay, it depends on a separate computational element to tell it when to open and close. Okay, kinematic linkages and cams replaced motion profiles and motors. Air dampers running this building. If this building is reasonably modern, you're using variable speed motors on the fans instead of dampers to control airflow in the building. It's just some of the examples of what happens when you look from this perspective of saying if there is information being transmitted, computed by mechanical components, don't do it. Okay, replace them. In order to do design, you need a context. And so the context that I deal in and the one I look at is what I call the unit machine. The unit machine establishes a domain of applicability. Knows what is your design methodology applicable to. So the definition is that the units, the elements of a unit machine, either directly exchange physical power or exchange material with little or no buffering. That represents what I call a unit machine. And the basic design issues are, if you select your unit machine too big, you end up having trouble handling the complexity. If you select your unit machine too small, you can't optimize because you've modularized too much and you can't do global optimization. So a fundamental design decision in any system is, what's my unit machine? And when I design the mechanical system, designing the unit machine is important. One of the reasons a lot of systems fail is that the machine design and the control are done, as if they had nothing to do with each other. Okay, so some designer will design a machine and then they'll say, okay, you control guys, now control it. And if this decision is made badly, the machine either will perform badly or unreliably because the unit machine was selected too large and you never could get a handle on it, or it will not perform well enough because you couldn't optimize it. Either of those. Here's an example from semiconductor manufacturing by way of a little disclosure. This comes from Berkeley Process Control, which is a company that I'm a co-founder of and still associated with. So this is internal stuff in that sense. This is a typical front end of a semiconductor machine. You can see a wafer. Typically, the wafer is taken in and out of the carriages that move them around and then placed into processing and in and out. And you've got these robots. This is a typical R theta Z robot. It goes up and down and it goes in and out. It goes around. There's an aligner here. There's no wafer on it, but that's what finds the center of the wafer. And if it has a notch, it will also find where the notch is. You want to handle these wafers efficiently, obviously. They're expensive. The throughput of these machines are expensive. This was a particular project at Berkeley Process Control in which the machine was designed but was underperforming. Okay, and the people who designed the machine came to Berkeley Process Control and said, hey, this is underperforming. With essentially no redesign of the machine at all, but a change in the control philosophy as to what was the unit machine, the improvement was 3.5 times. Okay, so almost a 400%, 350% improvement in performance. What was the issue? Even today, if you go into a semiconductor plant, you will find almost all the time, unless it's a Berkeley Process Control controlled machine, the robot will have its own controller. The notch aligner will have its own controller. The whatever kind of modules are used here will have their own controller. So the unit machines have been defined too small. Okay, and when you define them too small, for example, if you've got a robot handoff, like in this system with 2 robots, you've got to keep the robots separated. If the controller in robot A doesn't really know where robot B is, you've got large exclusion zones. That takes time. Okay, if you've got a single controller controlling all of them, you can do a robot handoff like this because the exclusion zone moves with the robot because you know where it is all the time. So issues like that are fundamental design decisions in terms of what constitutes the unit machine. And they make a huge difference. I mean, this is low-hanging fruit. You don't usually get this kind of difference, but you can. Okay, so control software for a unit machine needs access to all internal information. Sensor, actuator, states, commands. You have to have this information fast enough to use in control loops. Fast here, by the way, in a mechanical system, most of the interesting activity in a mechanical system goes on at the millisecond level. Okay, so most of the interesting things are happening roughly at the millisecond level. So that's the general time. There are a few interesting things like encoder events happening at the microsecond or faster, And then overall system operation, of course, something like that happens over several minutes in order to complete a full cycle of operation. So the time scales run from microseconds more or less up to minutes, where, as I say, the most interesting activity is mostly focused around the millisecond level. A couple of examples. So there's the wafer handling robot. The Denver airport fiasco is a good example of defining the unit machine too big. The design for the Denver airport when it was built, when did it go into service? 7 or 8 years ago? 92, okay, a little more than that. 15 years ago. So when the design was done 15 years ago, the baggage handling was going to be completely automated. Right? So you put a barcoded piece of baggage from the clerk onto the conveyor, and it was never touched again until it got to the right airplane. But this entire, from what I can tell, I was not inside this system, okay, but from what I can tell, this entire system was viewed as a unit machine. And it never worked. I mean, it would fling baggage out because the carts were going too fast, and the baggage would end up in the wrong place, and the carts would end up all focused on one end when you needed them on another. There were just no end to problems. It never worked. It cost the airport something like a year or a year and a half late opening up, which cost them something in the order of $1 to $2 billion because of that error. The baggage handling systems were basically ripped out and converted. When they finally opened the airport, United Airlines was having people carry baggage from the check-in to the airplane. But this was a good example of a unit machine being defined incorrectly. So you have two examples here, one where the unit machine was defined too small, and you get some really nice low-hanging fruit in terms of improving performance. The other where it was defined too big, and you get a total disaster, the system never worked. These are extremes, of course. You know, in the middle, things are a little more moderate, but the same general problems. Another interesting issue, dynamic definition of unit machine when you go from walking to running. Again, this is conjecture. I'm not sure it works this way, but I think it does. That is, when you walk, your whole body is a unit machine. You can freeze, you can stop, you know where all your joints are. I won't demonstrate, but when you run, you can't do that. And I think the unit machine for running is the legs. And then you separate basically navigation of the body and control of the legs. Because typically when you're running, if you find some unexpected change in the grade, you really can't correct it until the next step. And so again, conjecture. I think you've got a dynamic change in what the unit machine is to account for the difference in speed. You simply can't compute in the human brain fast enough to keep track of running, but you can for walking.
You're using your arms dynamically while you're running for balance.
Mm-hmm.
Yeah. Repeat the question.
Yeah, you're using your arms for dynamic balance in running, and that's absolutely true. So
Within each stride.
Mm-hmm. But if you look at that, again, you know, I'm not an expert, and I'm just kind of conjecturing on this one, that what you're looking at is within a stride pre-programmed behavior. And what changes is stride to stride. And that's a unit machine issue.
It seems to me that there's some counterexamples in, if you watch athletes play ball or whatever they're doing, but I don't want to have an argument. In that it would appear that they're controlling the whole torso, not just in response to real-time things happening as quickly as, you know, much less than a step interval. But I don't want to have an argument, but it seems like...
No, I will not argue at all. So the issue, to repeat, the issue is athletes, and I would add to that musicians. So if you look at that, and we're a little off topic there, but basically what's happening is you're using vast amounts of feed forward in those operations, which is why it's so hard to do. Because, quote, when you say learning, so learning, I play the guitar a bit, okay, or piano, or baseball, or what have you. When you're learning, what you're doing is using a huge amount of feed forward and pre-programming. And so to be a good baseball batter, for example, which is probably one of the single hardest things to do, right, is you have to make a judgment as the pitch leaves probably even before the pitch leaves the pitcher's arm. You have to make a judgment and then set the right program in motion.
Yeah, I think we're really talking about time constants, right? Because
absolutely.
Time constants for trying to hit the pitch ball is a lot smaller than the time constant for the runner carrying the ball. He sees things.
That's right.
And you see him react. So it's just a time constant.
Right. That's right. But the difference is, to use a unit machine on that time scale, we're into a different subject. We're into feedback control versus feed-forward control. Generally speaking, feedback control is nice because it's cheap. Okay? Feed-forward control is nice because you can get really good performance, but it's very expensive because you have to learn a lot. So just think about practicing your instrument, and you get feedback versus feed-forward, which I say, it's another seminar. but relevant here. Where do we go here? Mechanical engineers don't understand software, and software engineers don't understand machines.
They always understand software either.
Well, that's you said that, not me. Okay, so what I'll describe very briefly here is how I deal with this. This is basically how Berkeley Process Control designs its machines and how I teach design of machines. We need some way of describing control. We need a design language. We need to be able to design and document. We need a communication vehicle among all stakeholders. So we have to be able to talk not only to people like us who understand, C, Java, what have you, but also to people in manufacturing who are going to make this thing, people in marketing who are going to try to sell it, people in maintenance who are going to try to figure out how to fix it. Okay, and generally, I don't care what language you're using, it's unreadable. Okay, code is not readable by anybody, often not even readable by the person that created it. So that you need some language that's an abstraction layer above code to deal with. We use a fairly simple design model based on tasks and state machines. Okay, so no real good definition for tasks beyond the dictionary definition. A well-defined responsibility is a task. This kind of two-layer model, suitable for the unit machine we're talking about. Not suitable for a much more complex system. You need more layers. We use a hierarchical organization of tasks. The lowest level mapped to the mechanical system hardware. The higher levels are goal-oriented. Okay, so you get a model for tasks where these boxes represent tasks. A task, in computing terms, is a continuously running, simultaneously operating piece of logic. Okay, so all of these tasks are operating simultaneously. Okay, at least pseudo-simultaneously if they're all in one processor. Over here you have the software-hardware boundary. Up here you have the software outside world boundary in terms of communications. You've got an operator, you've got an internet, you've got a factory network, etc. Up at these upper levels, you have rather abstract issues. Okay, how do I make the most money out of some particular raw product that I'm processing? So think refinery. Okay, so every time a new tanker comes in, I've got a raw product that's different than the one I had before. Chemical properties are different. I have to figure out, what do I do with this stuff so coming out the other end I maximize value? Okay, way down at the lower end, I have to actually be able to deal with an actuator. Okay, so I have to be able to make some kind of actuator produce the amount of power that I want, and so on through here. Feedback control, supervisory control, giving set points to the feedback control, etc. This structure serves for organization, system organization. Tells you what you're doing. In the network sense, it allows you to look at these layers independently, put them together, work on them with different teams to some extent. We use finite state machines, so state transition logic to define what each task is doing. We do not allow nesting of state machines. So each task has just a single state machine. And the idea is, if you can describe the task with a single state machine, you can probably have something that's simple enough so that you can deal with it, complex enough so that it can do the job. It's a kind of trade-off between complexity and understanding. State machines are nice because if you want to get into a detailed discussion with somebody, it takes no more than 5 minutes to explain to somebody with any kind of technical background at all what a state machine is, and then you can be arguing over how the machine works. Why, if this sensor goes true here, do we do that operation? And you can be arguing why the machine and how the machine behaves, and you can be doing that quickly. Okay, implementation languages, portability, huge, huge issue. Clean syntax, you know, we live with what we get. We like it, but we don't always get it. Efficient footprint in operation, of course, getting less and less important as the price of computing comes down. Well documented. Portability is important because of the development stages of a machine. So you start off talking, when you're working on a machine, you start off talking about a machine that is some kind of prototype, you know, with sitting on a bench with wires in all directions and motors hanging out and what have you, and some PC sitting there running the machine. When you finally get into production, you know, you've got some embedded processor that is many, many generations removed from the PC. The other issue is the life cycle of a mechanical product. The life cycle of a mechanical product, anywhere from 5 to 20 years. Okay, whatever car you're driving, the base engine in that car could be as old as 20 years old. What's been changing on it is the controls and how it's operated. So you have to be able to take a basic machine and compare that to the processor generation time of about 18 months and be able to update that machine every 18 months or so. Typically, you update. Berkeley Process Control is a good example of the controller that they use as the core for all their products. I don't think in any generation has ever even used a processor from the same manufacturer, going from one generation to another. Yet all of that software has to be ported along. You need to focus on mapping design to software, the critical issue. How do you go from the state machine to the software is the critical issue here. You want to weaken the dependence on language, operating system, and the environment, and the hardware specifics. Okay, that will give you the best portability you can get. There is, you might call mythology in the real-time world that real-time means interrupts. And interrupts mean loss of hair. Right? Nothing is more frustrating than trying to operate and debug something in the interrupt domain of a processor. For most of the real-time work in a mechanical system, you can do it with cooperative multitasking. If, and one big if, you have to write non-blocking code. Okay? If you impose one stylistic rule, you can move from the interrupt environment to the cooperative environment, and you can save yourself a huge amount of development time and some hair. Okay, so the nice thing about it is this fits the state machine extremely well. So whereas a lot of people write real-time software if you're waiting for an event to happen, say a sensor to close, with a while loop, right, an empty while loop. So you put a while loop, you put a test for the condition, and then an empty statement, and you just sit there. Now, in an interrupt environment, you sit there for a while, and then you get an interrupt, and it goes away and does something else, and it comes back. In a cooperative multitasking environment, you can't do that, okay, because you're now hung in the cooperative environment. But if you move those kinds of decisions to the state machine level, A, they're visible to other people, and B, you can now do them cooperatively. Because in the state machine environment, all you have to do is return the answer to a question, do I need to do a transition now or not? All you have to do. Yeah?
I think you also need to break long computation. Because if you enter a long computation, then
long is in the eye of the beholder, of course. So long relative to whatever your critical times are, absolutely. But again, the state machine gives you a nice way to break a computation into pieces. So what computation time in terms of non-blocking means predictable. Okay, once it's predictable, then you can compare it to your specification.
Typically, non-blocking is just higher. But when you do our computation, you also need to.
Again, depending on, right, the question is, in non-blocking code, if you have a code that executes a long time, do you have to break it into smaller pieces? And the answer is, when you look at the interaction between your code and your timing specifications, you may have to do that, or you may have to get a faster processor. One of the big, and again, in mechanical systems, the accountants are in control. Okay, and the accountants are heavily focused on bill of materials. Software does not appear in the bill of materials. So if you look at the bill of materials for a piece of mechanical equipment, you will not find software. You'll find the cost of the ROM that's plugged in, right? But you will not find the cost of software. And that's phony accounting. Okay, because the cost of software, time to market, system reliability, etc., is heavily dependent on the speed of the processor and, along with that amount of memory. Okay? When the cost accountants get a hold of that, they look at the bill of materials and say, well, you've got a $4 processor in here. I'll bet you could use a $3 processor. Okay, and sure enough, they win that argument. And then in come the control guys, the software guys, and you have to go through heroics to make it work. And you have to play games of the sort you're talking about, breaking pieces up, doing calculations, just missing your deadlines by fractions of a millisecond. The system is unreliable, takes longer to get to market, etc. So there's a real mismatch between bill of materials accounting and accounting the real cost of a machine. By the clock on the wall, I think I'm about out of time here, so I'll just stop right there. There's more stuff in the same domain, but I think you get a flavor for how I'm looking at mechanical systems and how software is A, critically important, and B, you have to look at design methodology if you want to do successful design. And I think I'll just quit now and open for questions, discussions, etc. Thank you. Yeah.
Do you see value also in small machine units that are cooperating at the same level of peer-to-peer to achieve a goal?
That's a really good question. The question is, do I see value in small, independently operating mechanical units that operate in some peer-to-peer way? And the answer goes right back to the system definition and the unit machine definition. The answer is yes, if it's appropriate. Notice, think of a sensor, for example. Okay, so if I have a sensor that's smarter, that, for example, can do its own calibration, that can do its own fault diagnostic, that calibration fault diagnostic is, in some sense, offline activity. It's not crucial to the unit machine to know that sort of thing. If I can afford it in the particular machine, it's worth its weight in gold. On the other hand, if you look back at that wafer handling example, those robots were small, independently operating systems. And because they were broken apart like that, you couldn't optimize the overall operation of the machine. So the answer is yes, but with care. Great, thank you very much.